introduce the idea of rotational inertia and should have a pencil handy as we go through this. Um, if I want to take the pencil and accelerate it up or to the side or whichever way I want to accelerate it in translational motion, the inertia of the pencil is just its mass. And it doesn't matter how the mass is laid out along the pencil. Um, Still the same inertia that is occurring in Newton's second law of motion, equating the sum of the forces on the pencil equal to the inertia of the pencil times its acceleration. You can quickly demonstrate to yourself that the situation is a little bit more complicated for rotation. So if you take your pencil and try to rotate it back and forth this way, that's going to feel like a certain amount of force on your fingers. And if you think about that, that is you're rotating along an axis that's parallel to the long axis of the pencil, right? So think of how hard you have to push to do that compared to how hard you have to push to do that versus that. Okay. And it's all the same mass of the pencil, it's the same length of the pencil, the same diameter of the pencil, all those parameters are the same. But those forces that you have to exert to do that versus that versus that are going to feel different because the rotational inertia of the pencil is varying depending upon where the axis of rotation is. The more mass I have, the further away from the rotation axis, the greater the rotational inertia. So I've got to apply, as we're going to see in a little bit, as a torque. I'm going to have to apply a greater torque to get the same angular acceleration when I have a larger rotational inertia. So to accomplish this rotation. All right, so let's try to develop the mathematics to think about that. And we can think about it in terms of kinetic energy. So the kinetic energy of an object that is just rotating about a fixed axis. So I take our bowling ball and we want to rotate it about an axis along its axis of symmetry, say. So that bowling ball, or I'm sorry, bowling pin rather, um, we could get the kinetic energy of translation. If we just take the bowling pin and have it move uniformly along a fixed coordinate direction. I just add up all the individual pieces of the bowling pin. Each piece has a mass mi. Each has the same speed vi if it's translation, and just add it up for all the pieces, and I'll get a kinetic energy of translation. If instead what the bowling pin is doing is rotating about an axis, then this v is no longer the same for every piece. So every piece has its mass, it has its distance to the rotation axis. So this r sub I is the uh, perpendicular distance to the rotation axis, which will be the shortest distance to the rotation axis. So vi breaks up into ri times omega, where omega is the angular speed that our bowling pin is rotating at. So for the kinetic energy of rotation, I have a bit that depends upon how the mass is laid out relative to the rotation axis, and I have a bit that's the same for the entire body with the omega. So I can factor that into, I have a half, I have this summation over how the mass is laid out relative to the rotation axis, and then I have the angular speed squared. And this summation over the matter distribution is called the rotational inertia. And since Ri depends on distance to the rotation axis, rotational inertia depend upon your choice of rotation axis. All right. So this common factor, we'll go through a table of some frequently used values for rotational inertia. But I want to emphasize that this just depends upon the perpendicular distance to the rotation axis. So as we're going to see on the next slide, like vertical extent is not going to matter if the distance to the rotation axis is not changing for a point. So in that sense, like a uniform cylinder rotated about its long axis is the same as like a quarter rotated about its rotation axis through the center. All right. If this summation extends to a continuous distribution of matter, instead of just like individual particles, it's a think of it instead as a continuous distribution. Then you have a little calculus exercise set before you. The rotational inertia means integrate over the mass distribution weighted by the distance to the rotation axis squared. So rotational inertia is the integral of r squared over the mass. That's sometimes going to be sort of a weird variable to integrate over. Sometimes it works out, sometimes it's not going to. So instead, it probably would behoove you to change variables from a little element of mass dm into the density times a dv, and that's a volume integration. So in Cartesian coordinates, that's dx, dy, dz. So this is a triple integral. You would do it over each of the coordinates. It could be in spherical coordinates, could be in cylindrical coordinates, all sorts of coordinates, but this is a volume element. So instead of doing that triple integral, this is not a calculus class, it's a physics class, we are going to make use of table of common rotational inertias. So I'm going to talk about things that roll first. So a hoop that's going to spin around its central axis, or if it's not like an infinitesimally thin hoop, if it actually has some extent, then you're talking about an annulus. If the inner radius of the annulus goes all the way into zero, then you have a solid cylinder. Could also have for rolling motion a solid sphere or a hollow sphere here in G. For each of those cases, you're looking at a rotational inertia that is mass of the object times a radius squared or the radius squared. For the annulus, you have two radii and you weight them equally. So those are rotational inertia for things that roll. Hoop, all the mass is as far away from the axis as it can get, so that maximizes the rotational inertia. So the prefactor here, you can imagine it being a 1. If I go to a solid disk, the material on the rotation axis has no rotational inertia. So you can spin that for free, and that winds up giving you the prefactor as a half. If I have a solid sphere, then all of the mass along the rotation axis has no rotational inertia, and I have a smaller proportion far away as opposed to like a solid cylinder. And that integration winds up giving you a prefactor of 2/5, which is smaller than 1/2. And then if the sphere is instead a thin spherical shell, then I'm not gaining by having all of the matter along the rotation axis not contributing to the rotational inertia because most of it's empty space. And so instead, it's just a little contribution from the end caps where the diameter is running through. So I wind up with a larger rotational inertia for the mass and the radius. That's going to be something more like a hoop. So it's 2/3. And then if we're not considering rotation about an axis that the object could roll around, then you have like your pencil about an axis through the middle, or if it's a very thin cylinder, you can neglect the radial dimension and get a 12th ml squared. We also have results for a hoop about a diameter, and then something that'd be useful for like the rotational inertia of like a swinging door or something like that is a slab perpendicular to rotating about an axis perpendicular to the center. And these are all for uniform density objects. Uh, if the density is a function of position, then you're gonna have to go back and actually do the integration. Those aren't sort of common enough to be tabulated normally, unless you have a pretty exotic physics handbook at your disposal. So, common rotational inertias, this will be a useful table for you to go back and refer to. And then to extend that table to other cases, we have a mathematical result, the parallel axis theorem. So if the rotation axis does not pass through the body, but is still parallel to an axis that you know the rotational inertia for that passes through the center of mass of the object, then we can use the parallel axis theorem. So what that is telling us is, so I've got the sphere, and I know its rotational inertia about a diameter running through the sphere. So if it's a solid sphere, this is 2/5 m r squared. But now I'm going to take this ball and have it rotate about this external axis, but parallel to a diameter running through the center of mass of the sphere. Um, its rotational inertia about this axis, okay, is going to be its rotational inertia about the axis passing through its center of mass plus total mass of the object times the distance away from the rotation axis squared. It's a very handy result for finding rotational inertia in more complex geometries. As long as the axes are parallel, basically is just a little mathematical proof that you're just translating it over, and that's all you have to worry about. So that parallel axis theorem can extend the results you have in the previous table. So for example, for the rectangular slab, you have a result for rotational inertia for an axis passing through the center. But instead, if you wanted it to be at the corner, well, that's a parallel axis. So you would have a term that is the mass of the door times the distance you would find from the Pythagorean theorem to go from the corner to the center. Okay, not a big deal. And a generally useful result. Make your life easier.